All right, the last major topic in statistics that we want to talk about in BAS 471 is hypothesis testing. And this allows us to answer a few questions that making a confidence interval can't answer. And so it plays a relatively small role in an analytics practitioner's day-to-day life, I would say. And so I want to start out the discussion by talking about the presence or absence of a hot hand in basketball. So it's a pretty widespread belief among players and fans of basketball that there is such a thing as a hot hand. Basically, once you are in the zone, you heighten your ability to make baskets, make your ability to make free throws a bit better. There is such a thing that happens in basketball and maybe some other sports as well. And so there have been polls, there have been surveys that gauge the prevalence of this sort of belief. A few questions that we've seen before in past research. Some people were being asked, all right, is it important to pass the ball to someone in basketball who has just made several, like 2, 3, 4 shots in a row, because they're on a streak, they're in the zone here? And a separate question, a player that has a better chance of making a shot after having just made his last 2 shots or 3 shots than when he does after having just missed his last 2 or 3 shots. So 2 questions that were posed to fans and players alike. And for the first question, 84% agreed with that first statement. It's important to pass the ball to someone who has just made a bunch of shots there in the zone. And even more, 91% agreed that the player has a much better chance of making the next shot if they just made their last few shots than if they had just missed their last few shots. So there's a pretty widespread belief that whether or not you do or don't make a shot is relatively streaky. And so let's look at a specific example here. Klay Thompson had a very famous game back in 2016 where he scored a total of 60 points. And if we break it down into the sequence of his shots, representing a 1 as making the shot, 0 as missing, we can look at the entire history of his performance for that game. And so as we look through the sequence of hits and misses, we'd like to ask ourselves, okay, well, is this particular game evidence of a hot hand? And, looking into the sequence, we do see somewhat unusual streaks where we have 4 shots that were made sequentially. We have this long streak here where 6 shots were made sequentially. And so, it maybe looks like some evidence that, yeah, once you've made a shot or 2, maybe you're a bit more likely to make your next shot. And so maybe we are onto something. And so the question behind hypothesis testing is how can we use this data to help answer our question of interest here? And in order to do this, well, as business analytics practitioners, we want to be making data-driven decisions. So what is it specifically, maybe, that we could measure about this sequence that would clue us into the presence or the absence of a hot hand? So if we just kind of think out loud about what we might measure, well, could we measure maybe the fraction of shots made here? There's 44 total shots, 31 were made. And, that's a relatively high proportion. That's a pretty high hit rate for basketball here, but does that really clue us in as to whether or not there's a hot hand? Well, not really, because the presence or absence of a hot hand is really going to be tied into the ordering of the shots, and if we just look at the fraction of shots that were made, that doesn't really indicate whether or not, we have streaks or non-streaks in that sequence. So what else could we potentially measure? Well, how about the total number of streaks here? How often does the sequence go from 1 to 0, back to 1, back to 0, etc.? If there's going to be a hot hand, well, there should be relatively few streaks, where we have long strings of 1s, say all in a row, kind of punctuated by 0s here and there. But there's some other things we could potentially measure. Maybe the longest streak. In Klay's sequence right here, we had 6 shots that were made all in a row. Maybe that's highly unusual to see if we were dealing with a purely random sequence. Maybe that is evidence of a hot hand. Or we could measure something else. Maybe we could dive in and look at the places where we find one shot that was made, and then we ask, well, what happens to the next shot? Is it made, like in this case it is, or is it missed? So what fraction of shots that were made are immediately followed by another shot that was made? In this case, there were a total of 30 shots that were made. 19 had the next shots also being made, so 63.3% of those shots were immediately followed by another basket. So is that high? Is that evidence for a hot hand? Or is this value something that we would expect if the sequence of the ones and zeros here, the hits and the misses, were just purely at random? So that's what hypothesis testing is all about. We have some question about reality here. Basically, is there a hot hand in basketball or is there not? We have some data and we'd like to figure out, well, what should we measure about this data that'll clue us in to the true state of reality? And then how can we figure out, which of the two worlds are we living in? Are we living in a world where a hot hand is a thing? Or are we living in a world where it's just consistent with shots being made or missed at random? So let's revisit the idea of one of these statistics that we could measure, something we can measure from the data, the total number of streaks. Let's see what sort of progress we can make in answering the question of whether or not this sequence in particular serves as evidence of a hot hand. So what I've done is I've color-coded each of the ones and the zeros by either blue or black, just to make the ones and zeros stand out from each other. So if a hot hand really does exist, well, what would we expect in terms of the total number of streaks? Well, if a hot hand existed, we might expect to see really long streaks of ones, like what we do right here in this part of the sequence, kind of punctuated by zeros here and there. So if we were to look at the total number of streaks, and if we do for this particular sequence, there's 22 total streaks, 22 instances where we go from 1 to 0, back to 1, back to 0, back to 1, back to 0, etc. And so we just need to ask ourselves, well, is this ordinary? What would we expect for the total number of streaks if we were dealing with a purely random sequence, where what follows is completely independent of what just came before it? So we need to figure out some sort of method to glimpse what we would expect from a purely random ordering of these ones and zeros here. What would be ordinary for the number of streaks, and what would be extraordinary? What would really clue us in to a highly unusual number of streaks that would serve as evidence for a hot hand? So we need to figure out, well, how can we glimpse at other sequences that are being purely generated at random so that we know what to expect in terms of the number of streaks here? Well, we could use the sample command. We've talked about that with Monte Carlo simulation. If we want a sequence of ones and zeros, we could pick the ones and zeros at random by saying, okay, pick from ones and zeros, a total of 44 of them, since that's the length of the original sequence, with replacement, of course. But we know that, not the ones and the zeros don't have equal probabilities. Clay is able to make more than half the shots that he takes. And so we have to ask ourselves, well, what do we put in for the prob argument? What is the true probability that he'll make any particular basket? And that's not really a question that we can necessarily answer from this data. We know it's not 50% because he makes more than half of the shots that he takes. Maybe if we collected some more data, we could kind of nail down what that number is. Well, maybe or maybe not. It might be the case that this probability changes from one game to another based on the quality of his components. And even if we knew kind of what his long-term probability was of making a particular shot, that's not really answering the specific question that we have as to whether or not this sequence that we've collected is evidence of a hot hand or not. So even if we knew what his true probability was, it doesn't really directly address whether this sequence is an example of a purely random sequence or if it's evidence of a hot hand. What we'd like are sequences that kind of look like this, but that are generated purely at random. And so what's our solution here? Well, one clever thing that we can do with the originally collected data is to permute the original sequence. In other words, just randomly shuffle up the ones and the zeros in the sequence. And if we do that, if we randomly reorder the ones and the zeros, then we automatically ensure independence between the values in that sequence. So if we keep the number of ones and the number of zeros as is and just kind of randomly rearrange the ordering here, well, we preserve kind of what the sequence looks like in terms of the number of shots made versus missed, but we're able to ensure that the sequence of shots is just independent here. And so we could measure the number of streaks that we see in those randomly generated, randomly permuted sequences to get an idea of what we could expect in terms of the number of streaks if there was no sort of hot hand. And that's something that we can do in R pretty easily. If we take our original sequence and just convert it into a vector of ones and zeros, well, we can measure the total number of streaks with this kind of cool command in R called RLE, run length encoding. If we say RLE on our vector of data with the $ lengths, we get the run lengths, the streaks. So we started out with a streak of 2, streak of 1, streak of 4, 2, 1, 4. We see it matches up. And if we want the total number of streaks, well, we can just count up the length of this vector and then subtract 1 off from it. We don't actually know what ends up happening with this or not. Sorry, this one right here. We need to know, all right, well, is this a streak? Is this, a change from a 0 to 1? We don't really know what that incomplete streak is going to look like at the end, so we'll just kind of ignore that. We'll take off a -1, and that's where we get our 22 for the total number of streaks here. So we know that the fewer streaks we see in the sequence, kind of the more evidence we have for that hot hand. A streak or a hot hand would produce long streaks of ones punctuated by some zeros. So is this value of 22 unusual? Is this something that's not very likely to be seen when shots are made or missed just at random? So let's generate a random sequence. Let's run sample with our vector of original data values here. With no additional arguments, sample is just going to randomly reorder the values in the original vector. So here's an example of a randomly permuted sequence. And here's something that's kind of crazy. Notice how long of a streak of ones that we have. This was generated purely at random by just shuffling up the ones and the zeros from the original data. Kind of crazy. We expect just by pure randomness alone really, really long streaks sometimes. And in fact, if we ask for the number of streaks in this randomly permuted sequence, we get a value of 16, substantially fewer than the number of streaks in our original data. And remember, the fewer the streaks, the more evidence that there is a hot hand. And so we could repeat this procedure. We can take the original data and just randomly permute the ordering of the ones and zeros multiple times to build up an idea for what the number of streaks should be when we're dealing with purely independent sequences of shots. And so if we just put this into a for loop, say go through 10,000, say different randomly permuted sequences, we can build up an idea for what's ordinary in terms of the number of streaks versus what's extraordinary. And if we go and do this and make a table of the length of the number of streaks here, what we find is that 22 is actually, kind of on the high end of what we would expect from a purely random sequence. When we randomly permute the ones and the zeros from our original data, what we find is that, very often we see values of, say, 18, 19, 20 with a probability of 17, 13, 15%. Lower values were more and more evidence of a hot hand, and so this 22 is really kind of on the high side here. Making a histogram here, here's what the distribution of the number of runs looks like for purely random sequences with this number of ones and zeros as measured from the original data, and Clay's value of 22 is on the high side. Lower values for the number of runs is more evidence for a hot hand, and we see that that sequence that Clay generated really isn't evidence of a hot hand at all. 22 streaks is something that happens, kind of all the time when we're dealing with a purely random permutation of zeros and ones. There's definitely not really any evidence of a hot hand whatsoever. And so what we find is that by just cleverly reimagining that sequence of ones and zeros, the hits and misses that Clay made, kind of under the assumption that there is no sort of relationship between where the ones are and the zeros are, a random permutation, we find actually that he has more runs than the average random sequence. So if anything, his original sequence is really evidence against a hot hand. Evidence for a hot hand would have been very small values. He's on the larger side of things. All right, well, there are other ways of measuring if a hot hand does or doesn't exist. We didn't really find any evidence whatsoever from just looking at the total number of streaks. But what if we look at the sequence in a slightly different way? What if we focus in on the instances where he makes a shot and then ask, does he make the following shot? So in this case, the very first one in this sequence is followed by another one. So this first shot that was made is followed by the next shot, which was also made. We'll color code that one green. This one is going to be color coded red because the shot that was made right here is not followed by another shot that was made. So as we go through the original sequence, all the ones that are color-coded green are followed by additional shots that are made. Whenever we see a red one, that means the shot that was made was not followed by another shot that was made. So in total, there were 30 shots that were made. 19 of those shots were followed by another shot that was made as well. And so overall, about 63% that of shots that were made were followed by another shot that was made. So we can ask ourselves, well, is this evidence of a hot hand? It's kind of on the high side. If he just made a shot, chances are, a little bit better than 60% here, that he'll make the next shot. So is this evidence of streakiness, of a hot hand, that once you're in the zone, you've made a shot, you're more likely to make the next shot? Well, we can employ the same sort of strategy here. We can go and figure out, well, if the ones and the zeros were just arranged completely at random, what should the value of this fraction be? What fraction of the time, when he does make a shot, do we see another shot immediately follow? So once again, we can set up a for loop to go through 10,000 different permutations of the original sequence, just randomly shuffling up those ones and zeros, kind of measuring the fraction of time where a shot is made and immediately followed by another shot that was made. And so we can get a summary of what those fractions look like for purely random sequences. And so we see a pretty big variety, anywhere from 56% up to 87%. Let's look at a histogram here. And we see that Clay's fraction falls a little bit on the lower side, a little bit to the left of the peak. So what is this telling us? Well, let's put on our thinking caps and ask, well, what values for this fraction would be evidence of a hot hand? Well, if shots or baskets that are made kind of come in clusters here, come in streaks, then if Clay makes a shot and there is a hot hand, chances that he makes the next shot should be a relatively high value. So large values of this number here that we're measuring from the sequence would be more and more evidence of a hot hand. There's a high probability of making the next shot if he just made a shot here. And what we find in Clay's sequence is that his value is actually kind of on the low side. Evidence of a hot hand would be a value of like 75%. 80% of shots that were made are immediately followed by another shot that was made. We're finding that Clay's sequence is kind of the reverse. If anything, it's evidence against a hot hand because, we're getting fewer shots that were made next when we're looking at a shot that was just made than what we would expect actually from random sequences. So if anything, this is kind of evidence against a hot hand. And a lot of people find that's really quite surprising. If you go ask just the typical person on the street, hey, look at this sequence of shots that Clay made. Is this evidence of a hot hand? A lot of people say, yeah, these 4 ones in a row, these 6 ones in a row, these pairs of 3 ones in a row, that feels kind of streaky to us. But it turns out that if we sit down and do the analytics, think about it critically here, this sequence, if anything, is actually evidence against a hot hand. What we're seeing is that the stuff that we're measuring from the sequence is something that we measure all the time from purely random sequences. In fact, there's usually more evidence of streakiness from purely random sequences than what we're getting from Clay's sequence. And so this is going to be the role of hypothesis testing. Sometimes we have a very specific question about reality that we can't really use a confidence interval to answer. So is there a hot hand versus is there not a hot hand? Well, that's not something that we have a confidence interval procedure to help answer. And so this is where the hypothesis testing framework is going to be very useful. We have a specific question about reality. We want to figure out, all right, does the data support that hypothesis? Does it kind of work against that hypothesis? How can we use the data to answer the specific question? And so there's a good set of questions out there that we might want to ask that meet these conditions, things we can't readily answer from making confidence intervals that we've discussed before. that we can use hypothesis testing to help us out with. So if you're into predicting where the stock market is going to go, are the movements of stocks predictable at all? Or does it appear that the ups and downs from a day-to-day basis are purely at random? Something that we could use the hypothesis testing framework to help answer. We can collect data and see what the data suggests. If we have a more sophisticated question about comparing multiple groups, like are the return rates of 15 different product groups, the same? Are there any sort of differences? Well, we could use a hypothesis test to help us answer that. Does it look like, based on the data that's been collected, that it's just consistent with one overall return rate describing the return rates of these 15 top-selling products, or are there differences across the product groups? I almost became a traffic engineer actually before I became a business analytics practitioner. And one question I was always curious about answering was whether or not traffic patterns at an intersection have changed. The length of a red light, the length of a green light is tied into the current traffic patterns at the time. And so if traffic patterns change, well, you should update those stoplight timings. So what can you measure from data that is indicative of traffic patterns changing from when the timings were originally put into place? And so that's what we're going to talk about in this final unit here, really unit 13, is how can we run a hypothesis test and basically ask a question about reality that we'd like the data to help us answer. And for the most part, we've been answering these questions already. We've just been using confidence intervals to help us answer those questions. So whenever we come up with a question about the probability of some event occurring, we know how to come up with a confidence interval for that probability, and we can answer the question based on the confidence interval. If we want to know if there's a difference in probabilities between two groups, well, we know how to make a confidence interval for the difference in probabilities between group A and B, small little typo there. We have a question about the parameter of a probability generating distribution, lambda of a Poisson. We know how to make a confidence interval for that. We know how to make confidence intervals for mu's and for differences in averages between two different groups here. So for the most part, a lot of questions we have as business analytics practitioners, we can already answer with the confidence interval framework, but there's still a few questions that we have to answer with hypothesis testing, like the presence or absence of a hot hand, whether or not stocks move at random or if there's some sort of method behind the madness here. All right, so what we'll move into now is the basics of a hypothesis test. If we can't use a confidence interval to help us out, what is the procedure for running a hypothesis test? So all hypothesis tests essentially come down to the same set of 4 steps. 3 steps and really kind of a 4th optional step here. To run a hypothesis test, step 1 is always just coming up with what those hypotheses are. Hypotheses come in pairs. We have an alternative and a null hypothesis here, so we just got to set up the formalism behind that hypothesis test. And then what we do is we determine, well, what should we measure about the data to help us out in determining the outcome of that test. We're going to propose a test statistic, just something that we can measure from the data to serve as evidence one way or another for each of these 2 hypotheses. And then we'll go ahead and make our decision. We'll either determine a critical region for the test statistic or calculate the p-value of a statistic that we've measured from data that we've collected to come up with our answer. Basically, which of the 2 different hypotheses here does the data favor? And if the evidence doesn't favor the alternative hypothesis, if we retain the null in the terminology, then step 4, which is really optional but recommended, is to do some sort of power analysis to figure out, all right, if the null hypothesis was actually wrong, what's the chance that we would have actually even discovered the case with the data that we've collected? So let's go through each of these steps and talk about what role they play in the hypothesis test procedure and how we do this. So step 1 is just setting up the test itself, coming up with the pair of hypotheses that we'll use for the test. So every hypothesis test has an alternative hypothesis and a null hypothesis here. And to set it up, usually I find it easier actually to think about, well, what's the question that we'd like to answer? Usually the question that we want to answer goes in this alternative hypothesis. This is going to be a claim about the probability generating distribution that requires extraordinary evidence to really believe here. So if we're curious to know, is there a hot hand? Well, we're going to need evidence to suggest that there is. If there is going to be a pattern between where kind of stocks go on a day-to-day basis, up or down, that's going to require some sort of extraordinary evidence. Usually the question that we want to answer is going to be the one that goes into the alternative hypothesis. We'll call that HA. And the opposite, kind of the opposing viewpoint of the world, that's what we're going to put in the null hypothesis. That's just what we're going to believe about the probability generating distribution unless the data really convinces us otherwise. And so this null hypothesis will play a role. It'll allow us to kind of figure out what's ordinary versus extraordinary. And once we collect data and measure the appropriate test statistic from it, we'll be able to make our conclusion over what the data favors. Does it favor the alternative hypothesis? Do we have that extraordinary evidence? Or are we going to be stuck with just kind of going with the null hypothesis here? Now, this is stuff that you guys saw back in Stat 201, and it does take a bit of practice to really identify which claim goes in the null hypothesis, which claim goes in the alternative hypothesis, but with a little bit of practice, you'll get the hang of it. So let's just go over a few examples. Let's say that we did want to run the hypothesis test that examines whether or not there's a hot hand in basketball. So usually the claim that we're interested in investigating here, the claim that requires the extraordinary amount of evidence, that's what we put in the alternative hypothesis. So for this hypothesis test, is there a hot hand in basketball? The alternative hypothesis is that there is going to be a hot hand, kind of our research question. The null hypothesis, the opposite, is that there's no hot hand whatsoever. The sequence basically of hits and misses here is just completely at random. Let's imagine we were interested in establishing whether or not that a signal that we just collected from outer space shows that there's alien life out there. Well, obviously that claim requires a substantial amount of evidence, so the alternative hypothesis for this test would be that the signal is from aliens. The null hypothesis, kind of the opposite of that, is that the signal is not from aliens, the other viewpoint of the world. So the fact that we want to establish that the signal is really coming from aliens, that requires an extraordinary amount of evidence here. We place that in the alternative, the opposite, the null. What we'll believe, unless the data suggests otherwise, is going to be that that signal is just kind of noise. It's not from any sort of alien intelligence out there. All right, what about examples that are a bit more business analytics related? Well, let's imagine that we're dealing with a marketing firm and they claim that their ads have a click-through rate of 1 out of 40. That's relatively high in terms of click-through rates here. And let's imagine that you kind of doubt their claim. You think they're overstating their success. So how could we investigate this in a hypothesis test framework? Well, we need to figure out what should be our null and what should be our alternative hypothesis. Well, usually the claim that we want to establish goes in the alternative hypothesis, the claim that requires, evidence. And, to really make a case against this marketing firm, we need to establish with some sort of data that they are overstating their success. So in the alternative hypothesis, we're going to put in that P is less than 1 out of 40. That click-through rate is less than what the marketing firm is really claiming here. We really need evidence to establish that. In the absence of evidence, we should probably believe what that marketing firm is claiming. And so the opposite of P being less than 1 out of 40 in this case is that the firm is telling the truth and that the click-through rate is that 2.5%. All right, another example here. Let's imagine that we read that the Institute for Higher Education claims that people who have college degrees earn more on average than people with only high school degrees. It sounds pretty reasonable to us, but to really believe this claim that, making more money from a college degree versus a high school degree, that does require some evidence. And so we'll put that in the alternative hypothesis. If we imagine that the amount of money that people make with each of these 2 degrees is coming from some probability distribution, one for college degree owners, one for high school degree owners, well, we want to check to see is mu for the college PDF higher than mu for the high school PDF. That's the claim that requires a bit of evidence, and so that's the claim that we'll put in that alternative hypothesis. The opposite in this case is that the 2 averages are just going to be equal in this case. Without any sort of evidence one way or another, well, what should we believe? Well, just that the 2 averages are equal. When we collect some data, we can establish whether or not the average for college degrees is higher But that null hypothesis here, the opposite of college being higher than high school, would just be that the two are equal in this case. Here's another example. Let's imagine that we look at a map of a city, and each of these dots represent a case of lead poisoning. Looking at this, we might say, well, it looks like there might be some clusters here. Here's kind of a collection of dots that are pretty close to each other. Here's some dots that look to be pretty close to each other as well. Here we have big pockets where there's just no cases whatsoever, some sort of voids. And so maybe there is some sort of clustering in terms of lead poisoning. That would be a pretty interesting find to kind of establish. That would indicate that, hey, maybe there's a problem with water, or maybe some really old lead-based paint that's lurking around a neighborhood. So how would we set this up in a hypothesis framework? Well, to establish the presence of clusters, that's going to require some evidence. So in that alternative hypothesis, we'll say that, hey, there's some sort of clustering going on to these cases. We need evidence to establish that. Otherwise, we'll start out just with the assumption that the cases are being distributed just at random throughout the city. So the opposite of there being some sort of clustering is that the cases are just distributed at random. That's going to be in our null hypothesis, and we'll go with that until the data suggests that there really is clustering in here. If you're working for the analytics team at, say, AT&T, you might be modeling the number of calls that someone makes to customer service, and you might be interested in modeling that with a probability distribution. So you might like to know, okay, well, is this probability generating distribution a Poisson? Is it something different from a Poisson? Well, how would we set that up in the hypothesis testing framework? Well, in the absence of any other alternative distribution to a Poisson, we can proceed with this by just saying, sure, let's take our null that the probability distribution is a Poisson. We'll collect some data, and until the data suggests otherwise, we'll go with that Poisson assumption. So the null hypothesis that the data is coming from a Poisson is being kind of pitted against the alternative here that nope, it's something else that's not a Poisson here. We need some sort of evidence to establish that we're wrong in this Poisson assumption. We'll believe that it's Poisson unless the data suggests otherwise here. So when we set up this null and this alternative hypothesis, well, there's a bit of terminology that we need to get a bit used to. And this actually helps us out with running this test with a confidence interval. We have two broad types of tests. We have a two-sided test, and we have a one-sided test. So let's just represent the parameter of the probability distribution that we're testing by a placeholder called theta. It might be the probability of some event happening. It might be mu. It might be a percentile. It might be just something that we want to measure about this probability distribution. And when we set up our null and our alternative hypotheses, depending on what we write that alternative hypothesis test as, we're going to find ourselves in one of these two worlds. If our alternative hypothesis is that theta is just not equal to some parameter of interest, that's a two-sided test. So it might be bigger than theta naught, it might be smaller than theta naught, that proposed particular value of interest. We don't really care if it's bigger or smaller. We just are interested in if it's different than this particular value that we have in mind. That's that two-sided test. Two-sided because it could be higher, could be lower. We don't care. We just want to know if it's different. A one-sided test is when we really only care about values in one direction, either higher or smaller than that proposed value of theta naught here. So if our alternative is that theta is bigger than that value of interest, or if it's smaller than that value of interest, that's a one-sided test because really what we're only interested in establishing are values of theta that are on one side of theta naught, either values that are bigger or values that are a bit smaller. So how do we actually write these two hypotheses anyway? We have a null, we have an alternative. Until we get used to the procedure, we kind of have to learn a few tricks about, okay, well, what do we put in the null hypothesis and what do we put in the alternative hypothesis? And here are a few tricks that I found to be helpful over the years. So we've mentioned that the alternative hypothesis very often contains our claim of interest, what we need to use the data to help establish, the claim that requires a lot of evidence to really believe. And so when all is said and done, we find a few patterns in the way things are written. That null hypothesis is always going to have some sort of equal sign. So the PMF or the PDF is a Poisson distribution, or the sequence is being generated at random, or mu is equal to 5, the probability is equal to 10%. The null hypothesis always has an equal sign. The alternative hypothesis has something other than an equal sign. So the parameter we're testing is either less than, or bigger than, or just not equal to a particular value. So the sequence is not random. The probability distribution is not Poisson. Mu for college is bigger than mu for high school here. So when we do a hypothesis test, we basically have equal signs that populate the null hypothesis, and then sorts of non-equal signs that populate the alternative, either a less than, a greater than, or just a pure not equal sign. We actually don't use the less than or greater than or equal symbols in hypothesis testing at all. We always write the pair of hypotheses so that the null has some sort of equal sign and the alternative has these strictly less than, strictly greater than, or just pure not equal signs here. So with that being established, we can kind of make this connection between confidence intervals and hypothesis tests. And for the most part, a lot of questions that we do have in business analytics can readily just be answered by making a confidence interval. So for instance, let's imagine that we have this two-sided test. We'd like to know, okay, is theta equal to theta naught? Or is theta different than theta naught here? So if we're looking at the probability of some event happening, we might want to know, well, is the probability equal to 10%, or is 10% not the probability for this event? If we're estimating, say, the difference in mu's between two different groups, is the difference in mu's equal to 0? In other words, do they have the same overall average? Or is there some difference between these two groups? Is the difference not equal to 0 here? Well, how have we done this so far in BAS 471? Well, we've made that confidence interval. We make a 95% confidence interval, and then we check to see, is that proposed value, theta naught, a plausible value based on the data that we've collected? Does that value fall inside the confidence interval? If it does, well, that's the same thing as actually retaining the null hypothesis, saying that sure, theta naught's a plausible value for theta based on the data that we've collected, so we're in a world where we retain the null hypothesis. We haven't collected extraordinary evidence to suggest that the alternative hypothesis is the one that we should be going with. If, when we make that 95% confidence interval, we find that theta naught is not inside that interval, well, in hypothesis testing terminology, we go and reject the null hypothesis, and we favor the claim that's made in the alternative. Basically, if we find that theta naught is not inside that interval, we say that theta naught's not a plausible value for theta based on the data that we've collected. It looks like that theta is just not equal to that theta naught particular value that we have in interest. So this connection between the hypothesis testing framework and this confidence interval framework makes sense because since that confidence interval really does give a range of values that are plausible for theta based on the data that we've collected, we kind of have an idea on whether or not we have that extraordinary evidence that would suggest the alternative is where we want to go, or if that theta naught is just a plausible value for that parameter we're trying to estimate. Now, we can extend this confidence interval framework to when we have a one-sided test as well. If we're interested in knowing, well, is theta actually bigger than some value we have in mind, or is theta smaller than some value we have in mind, we can still make a confidence interval just with a little bit of a twist. Instead of doing our 95% confidence interval as like theta hat plus or minus 2 standard errors, what we can do is we can either find a upper bound for theta based on the data that we've collected, or a lower bound. And we'll be able to use prop test, binom test, or t-test to actually make a one-sided confidence interval to help us answer this question. So how do we go about doing this? Well, let's do a real-world example to establish a little bit of context. Let's look back at the wine data set that we've looked at a few times this semester. The wine data set is a data set that goes through a whole bunch of different varieties of wine. It measures the quality of the wine, either high or low, and we have a bunch of chemical characteristics of those wines, one of which is alcohol. So, quick review, let's imagine we were interested in testing to see if the average alcohol content of high versus low quality wines were the same or if they're different. So if we were going to stick with a confidence interval approach, we know how to do this. If we want to know, is there any difference in averages between high and low quality wines in terms of their alcohol content, we run t-test, and we get a 95% confidence interval for the difference. And in this case, we're 95% confident that the difference in averages between whatever probability distributions is making the data is somewhere between 1.5 and 1.65 here. 0 is nowhere to be found, so we say that 0 is not a plausible value for the true difference, and we say that we've established that there is some difference in the alcohol contents between those high and low quality wines. Low quality on average has an average of 9.9. High quality wines on average have 11.4, and it looks like this difference is statistically significant. So we've essentially used that confidence interval to run the test, where the null hypothesis is that the two averages are identical, the alternative hypothesis being that there is some sort of difference in those two averages. We've rejected the null hypothesis, and our data is favoring the claim made in the alternative, that there is a difference in averages between these two different groups. Well, what if we have a slightly different question? Let's imagine we were interested in comparing the citric acid contents of high quality versus low quality wines. And the specific question that we had was, is the average citric acid content for high quality wines lower than the average citric acid content for lower quality wines? Well, if we wanted to set up the null and the alternative hypothesis here, our claim, our investigation, where we want to be looking at, is that mu of high is being less than mu of low here. So that's going to be an alternative here that always has something other than the equal sign. The null hypothesis in this case always has the equal sign here. The average citric acid content for both high and low quality wines are identical. So writing this in a slightly different way, we could say that the difference between the averages is equal to 0 in the null hypothesis. The alternative hypothesis, mu high less than mu low, it would be just that mu high minus mu low is less than 0. So how can we get a confidence interval to help us answer this question? Well, we can just add in an additional argument to t-test, alternative equals to less. That's because this symbol that we see here in the alternative hypothesis is a less than sign. And so when we do this, we actually get an upper bound for what the true value of the difference is in averages. If we go and run t-test with alternative equal to less, we get a 95% confidence interval that looks like this, going from minus infinity up to this upper bound for the difference in averages based on the data that's been collected. So in this case, we're 95% confident that the true difference in averages is less than this upper bound here, less than minus 0.001. And so just as what we did for the other approach with the two-sided approach, we look to see if the value of interest is inside this confidence interval. Is it a plausible value based on the data that we've collected, or what? So in this case, our value of interest is just 0 here. We're interested in knowing if there is a difference. Specifically, is mu high less than mu low? So we check to see, is 0 inside this confidence interval? It's not, because all the values here are negative, so 0 is not a plausible value for the true difference based on the data that we've collected. And so we reject the null hypothesis. We go with the claim made the alternative here, that there is a difference, and specifically a difference of the sort that the average for the high quality wines is actually less than the average for the low quality wines here. The confidence interval for this difference only includes negative values here, and so the implication is that the average for the high quality wines is less than the average for the low quality wines here. All right, so we could actually use the bootstrap. We've talked about a bootstrap as an alternative procedure for making these confidence intervals as well. We just ask for a different percentile when we go and get our bootstrap estimates. So if we were to do the same example with the bootstrap, well, we could make a data set that just contains the high quality wines here, using the subset to get the citric acid values of just the ones that were high quality, make another data set for just the citric acid contents of the low quality wines, and then go and make bootstrap samples for each of them. Just sample from the original values that we've collected with replacement to populate the values in our bootstrap samples for the high values, the low quality values as well. and then just keep track of the difference in the averages every time we make a pair of bootstrap samples. So when we do this, well, if we have that less than alternative, we can ask for the 95th percentile of those bootstrap differences. Our 95% one-sided confidence interval in this case will go from minus infinity all the way up to the 95th percentile. And if we're using the bootstrap to run the hypothesis test, create that one-sided confidence interval, and we have that greater than alternative, well, what we would do is we'd go from the 5th percentile all the way up to infinity here, our 95% confidence interval for the difference in averages here. And we wanted, say, a lower bound, we would go from that 5th percentile up to infinity here. So we can still use the bootstrap if we want to make these confidence intervals, and so that allows us to essentially make a confidence interval to answer a hypothesis test. And so here's my opinion, and actually the academic literature and people are starting to get more on board with this, is that whenever we could use a confidence interval to run this hypothesis test, we really should. And a lot of the times we're in a world where we can use a confidence interval to answer our question. We know how to make confidence intervals for mu, an average, for p, the probability of some event occurring, differences in mu's, differences in probabilities between two groups. We know how to make confidence intervals for some parameter of a probability distribution. And we can do this hypothesis test just by making the relevant either two-sided confidence interval or one-sided confidence interval. It turns out that hypothesis tests aren't really quite as informative as if we were to just make a confidence interval for a range of plausible values for these parameters. And so what I'm going to suggest is to only use hypothesis testing for questions where you can't answer them by using a confidence interval. So it turns out that a lot of educators, a lot of statisticians, a lot of academic literature is kind of getting on board with this idea where hypothesis testing is a little bit outdated in this case. Yeah, there's a few questions that we really have to stick to for answering with the hypothesis testing framework, but the vast majority of questions out there we can answer just with confidence intervals. So if we can do this with a confidence interval, we will. If we have to do it with a hypothesis test, okay, we'll flesh out the rest of the framework to do so here. All right, so we have to run a hypothesis test. We can't use a confidence interval to answer our question. What's the next step? We've set up the null hypothesis. We've set up the alternative hypothesis. What next? So step 2 is coming up with a test statistic, something that we can measure from the data that'll help us figure out whether or not we live in the world described by the null hypothesis or the world described by the alternative hypothesis. So what we're going to do is we're going to assume that the null hypothesis is true until we have reasonable evidence otherwise. So what about the data should we be measuring to determine whether or not we have that extraordinary evidence to go with the claim made in the alternative, or whether or not we're living in that world that's being described by the null hypothesis? So the test statistic is going to serve as evidence, and statistic, remember, is just some value that we collect from the data itself, any number that we measure from data. And so very often we'll find ourselves in a world where there's a lot of plausible test statistics that could potentially clue us in as to which of these two worlds we live in. Sometimes there's actually an optimal test statistic, and the ones based on the MLE, the maximum likelihood estimator, ones based on averages, probabilities, are very often the optimal ones out there. So let's take an example, the hot hand, the example where we can't really use a confidence interval necessarily to answer our question. The null hypothesis would be that the sequential shots are independent. Basically, there's no hot hand. The claim that requires extraordinary evidence in this case is that there is some sort of hot hand. So there is some sort of association going on between whether or not someone makes a couple shots and whether or not they make their next shot. Well, what could we measure about the data that's been collected? Well, we've gone through those examples. We could measure the number of streaks that we see in that sequence. The fewer the streaks, the more evidence of a hot hand, that the ones all kind of come all in a row. We could look at the longest streak of shots made, or maybe the shots missed here. That's something we could measure from the data and use as our test statistic to see which of the two worlds we're living in. And maybe the thing that makes the most sense, actually, is looking at the proportion of shots that were made, which were immediately followed by another shot that was made. Larger values of this test statistic would be more and more evidence that, hey, there's some hot hand going on. If someone is in the zone, they're just making some shots here, they're more likely to make their next shot than otherwise. With the click-through rate example, well, if we were questioning whether or not this marketing firm's claim of having a click-through rate of 1 out of 40 was plausible, if we thought they were exaggerating their click-through rate, what could we measure about data that we could collect here to establish which of these two worlds we're living in? Well, one thing we could do is maybe collect information on the next 200 visitors. We could count up the total number of clicks out of those 200 visits. And we know that, okay, to establish this claim, we need some extraordinary evidence. The fewer clicks that we measure, the more evidence that we have is that the click-through rate is less than 2.5%. But there are other ways of going about measuring something from the data. We could actually sit down and look to see, well, how many visitors don't click that ad until we find that very first click. The longer that we have to wait for that first click to occur, the more evidence that we have that P is less than that 2.5% claimed by the marketing firm. There's no shortage of things we could measure from the data. We could look to see the number of visitors it takes for that fifth click to occur. The longer we have to wait, the more evidence that we have is that P is less than 1 out of 40 here. So for a lot of situations, sure, there's going to be a lot of things that we could measure from the data, a lot of possible test statistics that might serve as things we could measure that could indicate overwhelming evidence for the alternative hypothesis, or maybe not so much evidence. And so, depending on what we choose, we'll just have to go and measure what that value is from the data that we've collected and determine which of those two worlds we're living in. So a few more examples of what we could measure from data to use as test statistics for the different examples. We've talked about the clustering, the Poisson distribution, the differences in averages, but I think the gist is fairly clear. We just got to figure out something to measure from the data, some test statistic that'll clue us into which of these two worlds we're living in. So once we've determined what we're going to measure about that data, what do we do next? Well, remember the hypothesis test proceeds kind of like a jury trial, innocent until proven guilty. What we're going to do is assume that the null hypothesis is true and then figure out what values of the test statistic kind of separate the ordinary versus the extraordinary. What values of the test statistic are consistent with living in a world described by the claim specified by the null hypothesis, and what values of the test statistic are overwhelming evidence for the claim as specified in the alternative. So if we assume that the null hypothesis is true, the question becomes, okay, well, what does a sample look like? What values of the test statistic do we expect to see when the null hypothesis is true? What values of the test statistic are going to separate the ordinary, kind of the world as described by the null hypothesis, versus the extraordinary, the world described by that alternative hypothesis here? So what we need to do next is figure out what is the sampling distribution of our test statistic under the null. This expression under the null means assuming the null hypothesis is true, we need to figure out what samples look like, what values of the test statistic we expect when that null hypothesis is true here. So with the examples we've discussed, if there's no hot hand, what is the distribution of the number of streaks? If there's no difference in high school and college salaries, how big of a difference do we expect to measure when we go and collect data? If there is no clustering, and let's say we use as our test statistic the number of cases in any 2-block radius, when there is no clustering, what is the largest number that we would expect? If we're testing to see if the distribution of calls made to customer service is a Poisson, well, when the data generating distribution actually is Poisson, how do we expect the distribution of data values to actually turn out here? And so once we've established that, once we know what the sampling distribution of our test statistic is, what are the possible values we might observe, what are those respective probabilities, then that allows us to quantify, what's extraordinary versus what's ordinary. What do we expect when the null hypothesis is true, and what's really out of line to observe from data when the null is true here? So the way the hypothesis test proceeds is we go and collect some data, we measure a value of the test statistic from our sample, And then we see, well, is that out of line with what we expect to see when the null is true? If so, then we're going to favor the claim made by the alternative. However, if this is a value of the test statistic that we expect to see all the time when the null is true, then we'll stick with the claim in the null hypothesis. So with that click-through rate example, we're doubting the marketing firm's claim that the click-through rate is 1 out of 40. Our hypothesis test is frameworks set up so that the null hypothesis is that we believe the marketing firm unless the data suggests otherwise, that the click-through rate is 1 out of 40. The alternative, the claim we're trying to use data to establish, is that p is less than 1 out of 40 here. We'll use as our test statistic the number of clicks out of the first, say, 200 customers that have seen this ad right here. And we know that if we assume the null is true and that p is equal to 1 out of 40, the total number of clicks out of 200 is going to be well described by a binomial distribution, with parameters n of 200, 200 trials, and a p of 1 out of 40 here. So here is the sampling distribution of our test statistic when the null hypothesis is true. If the null is false in this case, and the claim made by the alternative is really describing the real world, p is less than 1 out of 40, well, we can see that very tiny values of the test statistic, like maybe a 0 or a 1, would be kind of out of line with p being equal to 1 out of 40. We'll talk about how to formalize that in a second. What if we were running that hypothesis test where we were curious to know, well, is the average salary for college students really bigger than the average salary for high school students? Or are we living in a world where both averages are about the same? Well, if we measure as our test statistic the number of standard errors the measured difference in sample averages is from 0 here, we can actually figure out what that sampling distribution of that test statistic is. It turns out it's a t distribution with some degrees of freedom. The possible values we might measure when we collect two samples from each of these two groups and measure the value of our test statistic looks like this t distribution. So we know that a value out of line would be something like a -4 or like a +4, something that we really don't quite expect to see when that null hypothesis is true and those two averages for those two groups are identical. So what do we do next? So once we know what values of the test statistic that we can expect to see when the null is true, we'll have an idea over what values of the test statistic are ordinary versus what are extraordinary, and that warrant going with the claim that's made in the alternative hypothesis. So one way to kind of complete the hypothesis test itself is to come up with a critical region of the test, basically a region of values that serve as extraordinary evidence, ones that lead us to go with the claim in the alternative hypothesis, go collect our data and see what we end up measuring. So a few bits of terminology about this critical region. We talk about the size of a critical region in terms of a Greek letter called alpha. We say this is the size of the critical region, and this is the probability that we would obtain a value in the critical region when we go collect data and the null hypothesis is true. And typically the standard is to take alpha to be 5%, and this is related to how often our hypothesis test actually makes errors. So we're going to allow ourselves a little bit of leeway, just like with a 95% confidence interval. We're comfortable with the notion that 5% of the time our confidence interval is going to fail to actually cover the value of the parameter we're trying to estimate. In a hypothesis test framework, we're going to be comfortable with actually rejecting the null hypothesis when it's true in 5% of instances. That's what this alpha 5% refers to. That's what we referred to as a type 1 error. And so when we design this critical region, a list of values that warrant rejecting the null hypothesis, we're going to try to design it so that there's a 5% chance of getting a value in the critical region when that null hypothesis is true. All right, so as an example, let's think about what the critical region might be for our click-through rate example. So the marketing firm is saying that, hey, 1 out of every 40 customers clicks on their ads, but we doubt that. We think that the true click-through rate might be a little bit less than that, so we set up the null and the alternative hypothesis accordingly. So since our claim that the true click-through rate is less than 1 out of 40 requires that substantial evidence that goes in the alternative hypothesis, the null hypothesis is all right, we'll believe the marketing firm unless the data suggests otherwise. We have in the null that p is equal to 1 out of 40. If we use as our test statistic, what we'll measure from the data, just the number of clicks out of 200 customers that visit the website, then we know that the sampling distribution of the test statistic is a binomial, counting up the number of successes out of a certain number of trials. And so we can immediately write down what values of the test statistic that we expect to see when the null hypothesis is true. Basically values from a binomial distribution with n of 200 and p of 1 out of 40. So what should our critical region be? What list of values warrant the rejection of the null hypothesis in favor of the alternative? Well, the fewer clicks that we see, the more evidence we have for the alternative. So we're going to develop a critical region that consists of a small number of clicks. So we can write that critical region as t being less than or equal to some value, some critical number of clicks here. We just need to figure out what value of c is appropriate to get a test that has a size or type 1 error rate of about 5%, the universal standard here. So if we make a plot of the sampling distribution of our test statistic, this binomial distribution, when the null is true, and if we're going to make our critical region for small values for the number of clicks, well, we can start out at 0 and ask, well, what's the probability of getting 0 clicks when the null is true? P-binom can help get us there. That's getting the value, probability of getting a certain value or something smaller. So P-binom of 0 gives you the probability of exactly 0, which is 0.6%. A little bit too small. We want the size of the critical region to be right at about 5%. So what if we took our critical region to be the numbers 0 or 1? What if we observed 1 or 0 clicks out of those 200? Well, p-binom of 1 gives us the probability of getting at most 1, and that gives us a probability of right at about 4%. That's pretty close to our target of 5. What if we had as our critical region, rejecting the null hypothesis when 2 or fewer of those 200 people clicked? Well, the probability of getting 2 or fewer clicks when the null hypothesis is true is right at about 12%. That's a bit farther away from our target of 5%. So we'll use as our critical region t being less than or equal to 1. Essentially, if 0 or 1 clicks occur when we go collect data, that is going to be extraordinary evidence here, sufficient evidence for us to reject the null hypothesis and go with the claim that's made in the alternative that the true click-through rate is less than 5%, or less than 1 out of 20 here. So the size of our test, if we use this critical region, is 3.9%. The probability of landing a value inside that critical region when the null is true. Close enough to that 5%. We can't get it exactly 5% due to the discrete nature of this test statistic, but that's good enough. All right, another example here, just to get an idea of how we can design a critical region. Let's, instead of using the total number of clicks out of 200 people, the number of customers it takes for the 5th click to occur as our test statistic. So same null and alternative hypothesis here. Our test statistic is now going to be the number of customers that do not click on the link before that 5th customer clicks on the link. And the reason for that slightly awkward phrasing is that we know what the sampling distribution is of this test statistic when the null is true in this case, counting up the number of failures until the 5th success is some flavor of a negative binomial distribution, specifically where size is equal to 5, counting up the number of failures to that 5th click, and the probability of success, the probability of a click being 1 out of 40 when that null hypothesis is true. So what should our critical region look like? Well, the longer we have to wait for that 5th click to occur, the more evidence we have that p is less than 1 out of 40. So we're going to take as our critical region values that are big, basically values of t that are greater than or equal to some critical cutoff here. And we'll choose this value of c so that the size of the test, the type 1 error rate, is right at about 5% here. So what we can use is that p and binom function to ask the question, well, what is the probability of getting a value of the test statistic of, say, 50 or more, 100 or more, 200 or more? And if we make a plot of the PMF, the negative binomial distribution, and we look at maybe about where that 95th percentile is, so the probability of getting that value or something bigger is about 5%, we find that if we take as our critical region a value of 357 or something bigger, that warrants basically substantial evidence, kind of overwhelming evidence, that p is less than 1/40th here. So if we have to wait 357 customers for that 5th click to occur, well, the probability of that occurring, that value or something bigger when the null is true, that only happens about 5% of the time. And so if we do find a value in that critical region, that is our extraordinary evidence for the claim in the alternative that p is really less than 1 out of 40. Getting a value that size hardly ever happens when the null is true, and so we'd reject the null hypothesis and go with the claim in the alternative. So there's a few more examples of setting up the critical region with some of these other contexts, but I actually want to move into the other and more preferred way of actually running the hypothesis test because critical regions are somewhat obsolete. It's a very binary decision of whether we do or do not reject the null hypothesis, and sometimes that is a little bit underwhelming. Sometimes we'd like a little bit more information out from the data that we've collected and exactly how much support that's lending for the alternative or lending to the null hypothesis. So instead of the critical region, we're actually going to focus on concluding our hypothesis test by using p-values. So the big issue with the critical region approach is that it actually depends on the size alpha that the experimenter has determined. So they usually are probably going to pick a value of 5%, but sometimes people choose a different value. And if you just kind of read up the results that they've reported back, if you had a different value of alpha in mind, you wouldn't necessarily be able to make your conclusion as to whether you would retain or reject that null hypothesis. So a slightly more flexible framework is to instead calculate the p-value of your test statistic. Now, this is one of the most important things that I think you can take out of BAS 471, this correct interpretation, very precise interpretation of what a p-value actually is. This is what is almost universally used in the literature and in everyday use among those people that are using p-values for hypothesis testing, so it's very important to get this interpretation right. So remember, when we conduct that hypothesis test, we assume the null hypothesis is true. We figure out the sampling distribution of our test statistic, the list of values and the possible probabilities that we might observe with those. The p-value is a comment on how likely our data is to be observed when the null hypothesis is true. So a few ways of actually phrasing it. The p-value of the test statistic that we measure from our data is the probability under that null hypothesis, assuming that it's true. The probability of observing that test statistic, or one that is at least as much evidence for the alternative as the one that you actually observed in your data. So this is really best illustrated with a few concrete examples. And so let's illustrate with a few examples, but first making the mention that the p-value is not going to be the probability that the null hypothesis is true. Just like how we said, when we have a 95% confidence interval, there's not a 95% chance that the parameter we're trying to estimate is inside that interval. That parameter has a value, we just don't know what it is. We don't use probability to quantify our ignorance about the world. This p-value is not a comment about the probability that the null hypothesis is true. It either is or isn't. We don't know what it is. We don't use probability to quantify our uncertainty about the world. The p-value is a probability about the data that we've collected, actually. So let's go through some interpretations here. All right, back to the click-through rate example. So we have data on 200 viewers, and 3 of those viewers ended up clicking on that ad. So 3 out of 200 is 1.5%, and that's less than the 2.5% that's claimed by the marketing firm here. So a little bit of evidence that maybe they're over-exaggerating their claim. So our question is that 1.5% far enough below the 2.5% to serve as extraordinary evidence that p is indeed less than 1 out of 40? So let's use the p-value to answer this question. So the p-value is the probability of observing our test statistic, or a test statistic that's even more evidence for the alternative, if in reality the null was actually true here. So if the null was really true, we would know that the distribution of our test statistic is a binomial distribution. Out of the 200 people that have seen the ad, how many end up actually clicking it? And so we can use this binomial distribution to figure out the p-value of our test statistic by figuring out the probability of observing our test statistic, exactly 3, or a value that's even more evidence for the alternative. Fewer and fewer people that click that ad, the more and more evidence we have for the alternative that p is less than 1 out of 40. And so that p-value would be the probability of observing a value of 3 or something smaller from this binomial distribution. We'll simply ask p-binom what that value is, and we get a p-value of 26% out. So what does this tell us? Well, let's do this interpretation. What does this p-value of 26.1% mean in layman's terms? So this is letting us know that if p was equal to 1 out of 40, there's a 26.1% chance of observing a sample with 3 or fewer clicks. So when the null hypothesis is true, this is the probability of observing our data, basically 3 clicks, or data that's even more evidence for the alternative, 3 or fewer. So we could say that, basically, in other words, there's a 26.1% chance of observing our data or data with even fewer clicks if, in reality, the marketing firm was being honest and their true click-through rate was 1 out of 40. That's a pretty likely number, a 1 out of 4 chance, basically, of observing our data or data that provides even more evidence for the alternative when the marketing firm is correct. And so in this case, we'd end up retaining this null hypothesis. We don't really have overwhelming evidence that p is less than a 1 out of 40. And so if we wanted to go with the more technical interpretation, there's a 26.1% chance of observing our data or data that's even more evidence for the alternative when p is equal to 1 out of 40. And so that just leaves us with saying, sure, null hypothesis. I don't have any reasonable evidence against you, so I'll stick with you. So what's going to be our threshold? How low does this p-value have to go in order for us to reject the null hypothesis? Well, there's a few standards that we have. The standard rule is to reject the null hypothesis when we get a p-value that's less than alpha. That type 1 error rate of the test that we get to choose, since we almost universally take that to be 5%, we reject the null hypothesis when we get a p-value that's less than 0.05. Otherwise, we retain that null hypothesis. So another example, let's look at this. Let's look at the money that's made with a college degree. So let's imagine that we have a random sample of 40 college students, and their average is $34,333, with a standard deviation of $8,000 here. So back when we were setting up the hypothesis test, the null hypothesis was that the average college and high school salary was the same. The alternative was that college graduates were making a bit more. So in this case, if we know that the high school average is 30,000, this 34,000 is quite a bit above, so is that substantial evidence to go with the claim made in the alternative, that the average is indeed greater for college graduates? Well, our test statistic we've been taking as the number of standard errors that the college average was away from the high school average. And so converting this into the number of standard errors, taking the difference in averages, dividing it by our formula for the standard error, we find that the average college salary is right at about 3.4 standard errors above the high school average. So is this a value that we observe all the time when the null hypothesis is true and the averages are identical? Well, let's get that p-value. When the null is true, and we're dealing with equal averages here, basically if we know that the college average is the same as the high school at 30,000, the number of standard errors that the sample average is observed to be away from that 30,000 is going to be well described by a t-distribution with 39 degrees of freedom. So what is the probability of getting our data, a test statistic of 3.4, or data that's even more evidence for the alternative, basically larger and larger salaries, larger and larger values of this t-statistic? Well, that can be given to us by pt. So pt tells us the probability of getting a 3.426 or something smaller. 1 minus that would be the probability of getting that value or something bigger, and we find that this works out to be 0.00073. So since that's less than the standard 5%, we would reject the null hypothesis, and we would say that we have extraordinary evidence that the alternative hypothesis is the one that's describing reality, that the average salary for college students is higher than the average for high school students. So we can be a little bit more careful interpreting that p-value in layman's terms. Basically, we have this p-value of 0.073%. So what does that tell us? Well, it's telling us that if the null hypothesis were true and the average amount of money made with a college degree was $30,000, the same as high school students, there's only a 0.073% chance of observing a sample where the average salary is $34,333 or something higher, basically what we measured in our data, or a value that's even more evidence for the alternative. So because there's only a 0.073% chance of observing our data, or data with even a higher average when mu is equal to 30,000, that leads us to overwhelmingly reject that null hypothesis and go with the claim in the alternative. It's just way too unlikely to see a sample average like this when the null hypothesis is true. So a few more examples in the notes here. Once you start getting used to that interpretation of the p-value, kind of understanding that, hey, this is a comment on how likely it is to observe our data when the null is true, that allows us to pretty easily make that decision on whether or not we retain the null hypothesis or go with the claim that's made in the alternative. So tying this back to our original example, did that one sequence of hits and misses that we have from Clay Johnson, does that serve as good evidence of a hot hand? Well, if we go and calculate the p-values of statistics with the hot hand with this data, we don't really find any evidence whatsoever. So I think the most compelling test statistic in this case was to go and look at the 30 baskets that Clay made and then see what fraction of those shots were immediately followed by an additional basket. Well, 19 of those 30 values were. But it turns out that if you go and get the p-value of this test statistic, basically if the shots really were just ordered at random, what's the probability of getting, say, at least 19 of those shots made immediately following a basket that was made? That p-value turns out to be about 96%. So if the shots were truly just sequenced at random, there's about a 96% chance that we would have seen at least 19 baskets immediately made or following a basket that was made here. So much, much higher than 5%, we'd retain that null hypothesis. This really isn't any evidence whatsoever for that hot hand. Now, if you're a big basketball fan and highly disagree with this sort of analysis, people have really studied this in the literature here. And so I have a few links, a few YouTube videos that really dive into not only this example, but then also additional examples that talk about the presence of a hot hand. The upshot is that right now, I think taken as a whole, the evidence suggests that the hot hand effect probably is real, but it's a fairly weak effect overall. Not nearly as strong as effect as most people and most fans of basketball really think that it is.